Today we'll go over Taylor series and Maclaurin series. And please make sure you have watched my related lecture video before you proceed with this lesson. Now, in my lecture video, I believe I developed Taylor series and Maclaurin series as the special case, which is true, okay? Maclaurin series is actually a special case of Taylor series. I can write it this way, that Maclaurin is actually a special case, a subset of Taylor series. Okay, now, however, the way I teach you now is the other way around. We will first make ourselves get used to deal with Maclaurin series, and then after that, we expand that to Taylor series. Now, what is Maclaurin series? Maclaurin series is the series expansion around zero. Around zero. Okay, when I say around zero, then it's the following. Suppose the radius of convergence is 1, right? Then the Maclaurin series we use to approximate the function only valid between -1 to 1, which is the interval of convergence centered at 0 with radius 1. Okay, so we can use the series that we get here to approximate the function only if the x is between -1 to 1. Now, suppose we have Taylor series at x equals to a, and we have that the radius of convergence is 1. Then it means this series expansion, this Taylor series, can be used to approximate the function as long as the x is no more than, actually less than 1 from a. So at most a plus 1, at least a minus 1. Okay. Now that's what it means, that's what it has to do with the radius of convergence and how we will use this series approximation to represent the function. Now, there are some functions that our textbook already gave the Maclaurin series approximation, the Maclaurin series, and let me write them here. The first one we already knew. We already know that's the geometric series. That's the sum from n equals to 0 to infinity of x to the n. That's basically 1 plus x squared all the way with radius of convergence 1. And together with that, if you remember, we have 1 over 1 plus x squared. You know what? 1 plus x first. 1 plus x. This is the alternating series, x to the n. So 1 minus x plus x squared, and so on and so forth. Okay, the radius of convergence also 1. And then we have 1 over 1 plus x squared equals to, so I think you want to write this down, at least on the separate sheet of paper, because these are the series representation that I allow you to quote directly without the need to prove in your test. That's right, n equals to 0. So I can modify this to be from 1. Basically, this is x minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4 and on. And because we developed that from geometric series, the radius of convergence still 1. Now, tangent inverse x is the integral of 1 over 1 plus x squared last time, right? So when n equals to 0, that's x minus x cubed over 3 plus x to the 5th over 5, x to the 7 over 7, and on. Again, the radius of convergence is the same. What else? There's one more. As I remember, we have one more. Oh, this one. Uh, 1 over 1 minus x quantity squared, which is the derivative of 1 minus x. So this will be, actually start from 1 instead of from 0. N times x to the n minus 1. So 1 plus 2x plus 3x squared plus 4x cubed and so on and so forth. The radius of convergence is equal to 1. So this is the list of power series representation that I allow you to code without proving. Okay, that's the power series representation from section 11.9. Now, anything outside of this list, except the one you see later on from 11.10, then you have to prove. Okay, now from 11.10, the power series representation, I should say the Maclaurin series, are first e to the x, which is the summation from 0 to infinity of x to the n over n factorial, which is when n equals to 0, 1 minus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and on. The nice thing is the radius of convergence is infinity, which means it applies for any x. sine x has this Maclaurin series extension. This is x to the 2n plus 1 over 2n plus 1 factorial. Now, take a look. The difference between sine x and tangent inverse x. Sine x and tangent inverse x. Sine x has that factorial on the denominator. Tangent inverse x does not. Okay. Now the expansion will be when n equals to 0, that is x, and then minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial and on. The radius of convergence is infinity. Now, the cosine, as you can see, is basically the derivative of sine x, right? So imagine if you take the derivative of that sine x. And I will get x to the 2n over 2n factorial. Okay, that would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And on, the radius of convergence is infinity. Okay, so only these 3 functions that I allow you to code without proving in your test later on. Okay, now let me prove one of them using the pattern that we have up here for Maclaurin series. Okay, this is Maclaurin series. Let's say, for example, I prove the one for sine x, Okay, okay. So for example, show. Is it what they do on the book? I don't really want to do what the book already has done. Oh, the book has done. Our book actually has done all 3 of them. Yeah, our book has done all 3 of them. Uh-oh. Show that maybe find, maybe instead example 1, find Maclaurin series for y equals to e to the x, or maybe fx equals to e to the x. It's more into procedure, though. It's more into procedure. So be patient with me. Okay. Solution. Notice the pattern for Maclaurin series. So fx equals to f0 plus the first derivative at 0 over 1 factorial x to the 1. The first derivative 1 factorial x to the 1. Now we don't have that with here because 0 factorial is 1, x to the 0 is also 1. Okay, so for the constant, you just follow whatever that is. Okay, and then I continue plus the second derivative at 0 over 2 factorial x squared. Okay, you see, if that's the second derivative, you divide by 2 factorial for x squared. Okay, and so on and so forth. Now, before I really go on with this finding the Maclaurin series extension, the Maclaurin series for this e to the x, I need you to be aware that if you only take the first two terms here, this is actually linear approximation for fx around x equals to 0. Do you notice that? And for Taylor series, okay, let me just write it down. For Taylor series, that's fa plus f prime a over 1 factorial x minus a to the invisible 1 plus f double prime a over 2 factorial x minus a squared, and so on and so forth, right? If you take only the first two terms, this is fa plus f prime a over 1 factorial, that's 1, right? Times x minus a. This is linear approximation for fx around x equals to a. I wonder if you realize that. Now, I mean, linear approximation is something you learn in Calculus 1, right? Linear approximation is something you learn in Calculus 1. Let me check again. Which section is that? Something to do even before Newton's method. Give me a second. I'm looking for that. Where is that? Give me a second. I'm looking for it. Chapter 2. Oh, 2.9. 2.9. In section 2.9. Okay, in section 2.9, we learn linear approximation around of fx around x equals to a. Okay, now it turns out to be that linear approximation, just the truncation of Maclaurin or Taylor series to the linear component only. Okay, now you may have heard also something called quadratic approximation. Quadratic approximation, basically, if you truncate that at the degree of 2. Cubic approximation, if you truncate that at x to the power of 3. You see what I'm trying to say? Okay, linear approximation when you have the linear part left, right, to the power of 1. Quadratic if you have degree of 2. Cubic if you have degree of 3. Okay, so it's just like how far do you want to approximate that? Okay, now that's just a little preview of what you to relate to the material that our textbook does not cover explicitly. Like quadratic approximation, our textbook does not cover it explicitly. Okay, our textbook does not cover explicitly quadratic and cubic approximation. Now, sometime in the past, Dr. Alwash, who was a part-timer at UCLA, I'm not talking shit about him, okay? I'm just telling you what happened in the past. We have been using Stewart's textbook since I was hired, or even before that. Okay, but somewhere in between, Dr. Awash want to change our textbook, would propose to change our textbook to something else, Rogowski, which was used at UCLA. And it is because James Stewart's textbook does not cover quadratic approximation. Okay, now, and I happen to be the one teaching calculus 3 at that time. I say that quadratic approximation is just a small section that we can easily cover that in calculus 2 if you want to. That's just one extra handout, you know. Now, he wanted to cover that in calculus 1. I said, well, if you want to teach that in calculus 1, fine. Okay, but the way I see is that that's just a special case. The quadratic approximation is just a special case of Maclaurin and Taylor series. Okay, so the reason James Stewart did not cover that explicitly is because, well, if you want to do quadratic approximation, just stop at degree of 2. Okay, if you want to do cubic approximation, just stop at degree of 3. Okay, now that's a little introduction to this Maclaurin series, which you have seen in the past. Okay, I basically want to say that you have seen this in the past. At that time, you stop at degree of 1. Now we keep on going. Okay, now, then how do we develop the Maclaurin series for fx equals to e to the x? So fx equals to e to the x. This is how you do it. Okay, what is f0? That's e to the 0, which is 1. Okay, notice that I start from here. Notice that I start from here. Okay, now from there, you will do two things. Find the value at 0 and find the derivative. Is e to the x. Now, once you get the derivative, then find the value again at 0. You see what I mean? And then from there, you do the derivative again. And then find the value at 0. I know you know how to do this. I'm teaching you how to organize your informations. Easier to read, not only for me. I want to be easy to have easy time to read your work, right? But if I have easy time to read your work, it must be because you have easy time to organize that. Okay. Now, then, so you see from here, we have that some pattern that the nth derivative at 0 is always 1 for fx equals to e to the x, right? Now, therefore, the Maclaurin series for e to the x is given by f0, which is 1, plus, maybe I write it this way, in summation notation. N equals to 0 to infinity, and then it should be f, the nth derivative at 0 over n factorial x to the n, right? But the derivative of the function at 0 is always 1. Which if I expand from n equals to 0, that will be 1 plus x over 1 factorial, which is 1, plus x squared over 2 factorial, which is 2, x cubed over 3 factorial, which is 6, and so on and so forth. Okay, and you can observe this thing though. You can observe that if you do the derivative of this series here, the derivative of this is this guy. The derivative of this is this guy. The derivative of this is this guy. So this is a function whose derivative is just itself. Right? And the only function, actually there are two functions. The only function whose derivative is itself is e to the x. There are two functions. Maybe I say it out. There are two functions such that f(x), f prime x equals to fx. Can you tell what's that? One of them is e to the x. What is the other function? What is the other function whose derivative is itself? Imagination. Nobody knows? fx equals to 0. Okay, those are two functions whose derivative it's itself. Well, anyway, how do we find the radius of convergence? We apply ratio tests. Okay, we apply ratio test by ratio test. So the next term, which is x to the n plus 1 over n plus 1 factorial, divided by the current term in absolute value is equal to x over n plus 1. But this will go to 0 as n goes to infinity, right? Now this is less than 1. From there, we know the radius of convergence is infinity. It's always 0. The ratio always converges to 0. Okay. However big your x is. Once you tell, oh, my x is 10,000, well, eventually your n plus 1 will be much, much larger than 10,000. Okay, now how about sine x? Sine x, our textbook went over that. Let's do cosine x. Let's do cosine x. For example, find Maclaurin series for fx equals to cosine x. Okay, solution. If we can quote, if we use the expansion for sine x, which is now the derivative of that sine x is cosine x, but that's also the derivative of this infinite series respect to x. Okay, now as long as it is within the radius of convergence, then the derivative of the series is the series of the derivative. But the derivative only applies to x, right? You see that? Which will give us, if I continue, so cosine x is equal to the infinite series from 0 to infinity, -1 to the n, derivative of x to the 2n respect to x is x to the 2n plus 1 is 2n plus 1 times x to the 2n over 2n plus 1 factorial, which is 2n plus 1 times 2n factorial. That's how we get that's x to the 2n over 2n factorial. Okay, that's if we use sine x. I will give you the ground up development for cosine x later on. But suppose we use sine x, this is what happened. I want you to be aware of some side note, which I don't even want to write it down, is this. Do you remember that sine x is an odd function? Right? Sine x is an odd function. So you see that the exponent for the variable in the Maclaurin series is always odd. Okay. While the Maclaurin series for cosine x, that's an even function, right? You see that the variable always have even exponent. So I hope that enables you to remember the expansion faster. Okay, now my test is open book, right? So yeah, you can just look at the book. But what I mean is, like, if you want to do it even faster, you better memorize it. Okay, you better memorize it. Okay, now, but if not, if we build the Maclaurin series ground up, so from very, very bottom, then we can do it this way. Okay, so we start with fx equals to cosine x, right? Now find what is f0. F0 is cosine 0, that's 1. Now then do the derivative. That's negative sine x. F prime 0 is negative sine 0, that's 0. The second derivative is negative cosine x. That's negative 1 here. The third derivative, that's sine x. The third derivative of the function at 0 is 0. The fourth derivative is cosine x, whose value at 0 is 1. Now, I hope you start seeing a pattern. I hope you start seeing a pattern. What kind of pattern? The pattern is as the following. That the coefficients, the Cn will be 1, 0, negative 1, 0, 1, 0, negative 1, 0, and on. Okay. Now, then we can see it this way, that this is the series from 0 to infinity, negative 1 to the n. Okay, but we will only take the odd terms. So let's say this is the first term, this is the second term, the third term, the fourth term, and on. Okay, so you see for the coefficients, right? This is our C1, C2, C3, C4. It's supposed to be C1 is 1, C2 is 0, C3 is -1, C4 is 0, and so on. But because it's 0 terms, I will just ignore them. After all, I have that pattern. I keep on skipping the even ones. Okay, so I will take only the odd terms, but then the exponents for the x then will be, when n equals to 0, the exponent is 1. I'm sorry. No, when n is when the exponent is 0, is 1, and then this is when, I'm sorry, I should say that this is C0, this is C1, this is C2, this is C3. I think that's better, right? So the coefficient for the 0th exponent is 1, coefficient for the third exponent is -1. Okay, so the denominator here will be 2n plus 1 fact, I'm sorry, 2 fact n factorial, 2n factorial x to the 2n. Because it's supposed to look like this: 1 plus 0x minus 1x squared plus 0x cubed plus 1x to the 4th. You see? So instead of dealing with the zeros term, I only pick this guy, this guy, this guy. Okay, of course, with over 1 factorial, over 2 factorial, over 3 factorial, over 4 factorial. But the 1, 2, 3, 4 factorials comes from the exponent with factorial, right? If the exponent is 3, then you have 3 factorial here. Okay? Now then I will go on. Oh, well, basically, I tried to explain why we get this formula. And that's basically what we have. Maybe I write it that way first here. So it will be 1, okay, plus 0x minus, for 1 factorial, minus 1x squared over 2 factorial plus 0x cubed plus 1x to the 4th over 4 factorial plus 0x to the 5th minus 1x to the 6th over 6 factorial and on. Now, if I ignore the 0 term, it will be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. Okay, now you can see that it is actually 1 over 2n factorial x to the 2n, right? And n starts from 0 to infinity. You see that? -1 to the n. That's how we get that, right? Now, how about the radius of convergence? We check the radius of convergence by doing ratio. Okay, now the next term is 2x to the 2n plus 1 over 2n plus 1 factorial divided by x to the 2n over 2n factorial. That is x to the 2n plus 2 over 2n plus 2 times 2n plus 1 times 2n factorial times 2n factorial over 2x to the 2n. That is equal to x squared over 2n plus 2, 2n plus 1. Now, as n goes to infinity, this goes to 0 for every x. Therefore, the radius of convergence is infinity again. Now, okay. So these are the three Maclaurin series that I allow you to just quote. How about other Maclaurin series? Let's say I do number 5. Okay, Maclaurin series for fx equals to negative 1 minus x to the negative 2. Okay, so solution fx equals to 1 minus x to the power of negative 2. So f0 is 1 to the negative 2, that's 1, right? Okay, the derivative will be negative 2 times 1 minus x to the negative 3 times a negative 1 that comes from the derivative of negative x, right? Derivative of 1 minus x. It's negative 1. That is 2 times 1 minus x to the power of negative 3. Now, f prime 0 will be 2. Is it right? The next derivative, that is negative 2 times negative 3 times 1 minus x to the power of negative 4 times negative 1. That is 6, 1 minus x to the negative 4. So f double prime 0 will be 6, which, by the way, is 3 factorial. This is 2 factorial. This is 1 factorial. Okay. The third derivative of x, let me do it one more time. This will be negative 24 times negative 1 minus x to the negative 5 times negative 1. That's 24, 1 minus x to the negative 5. So f third derivative at 0, that's 24, which is actually 4 factorial. So my Maclaurin series for that function, fx, which is 1 minus x to the power of negative 2, has Maclaurin series that will be, you see, the nth derivative at 0 is equal to n plus 1 factorial. Is it right? Do you notice that? Okay, now then this will be the nth derivative at 0 is n plus 1 factorial over n factorial x to the n, which if we cancel the top and the bottom, this is n plus 1 x to the n. Is it okay? Which I somehow think we did that problem. We have that up. No, we don't, huh? Oh, here. We have that here. You see that? We have that here. Let's compare. Let's compare. The series here start from 1, but this is n x to the n minus 1, right? Okay, compare that with this. Compare that with, if I start from 1 instead, okay, this will be n x to the n minus 1. You see, if I start from 0, then it will be 1x to the 0 plus 2x to the 1 plus 3x squared, right? Which is actually the same expansion if you write this one out. Okay, so this question is not like something new. In fact, the geometric, the power series expansion we got from geometric series also tell us Maclaurin series. Okay, this is what we get from section 11.9 for x1 minus x to the power of -2, which is 1 over 1 minus x being squared. Let's do number 9. Maclaurin series for fx equals to 2 to the x. Solution. Fx equals to 2 to the x. So f0 is just 1. Oh, that one is easy. How about the first derivative? That's 2 to the x times ln x. Yeah, ln x. No, not ln x, ln2. What am I doing? So f prime 0 is ln2. If you do the derivative again, then you will get 2 to the x ln x times another ln x, ln2. I hope we start seeing some pattern. ln2 being squared. Okay, let's do one more time. So derivative of 2 to the x ln2 squared, the derivative of that will have another ln2. So in general, the nth derivative at 0 will be ln2 to the power of n. Okay, so fx, which is 2 to the x, has the power series, Maclaurin series, n equals to 0 to infinity, of ln2 to the n over n factorial x to the n. Okay, which if we want to write it out, that will be when when n equals to 0, that's 1. When n equals to 1, that's ln 2 over 1 factorial x plus ln 2 squared over 2 factorial x squared ln 2 cubed over 3 factorial x cubed, and so on and so forth. How about the radius of convergence by ratio? Ln 2 to the power of n plus 1 over n factorial, n plus 1 factorial x to the n plus 1 divided by ln 2 to the power of n x to the n over n factorial. This is equal to ln 2 times x over n plus 1, which is convergent to 0 as n goes to infinity. So the radius of convergence is infinity. Okay, so this is the Maclaurin series for 2 to the x. Actually, from here we notice that the Maclaurin series for the Maclaurin series for fx equals to b to the x will be ln b natural log of b to the n over n factorial x to the n, right? And the radius of convergence, is also infinity. Why? Because by ratio, gada boom, we have ln b times x over n plus 1. But this will converge to 0, right? Okay, so call this a side note. Call that a side note. How about Taylor series? Now I change gear to Taylor series. Let's say we do number, let's say we do number 15. You know what? Let me do number 13, number 13 first. Let's do number 13 first. Taylor series around a equals to 1 of fx equals to x to the 4th minus 3x squared plus 1. Solution. Fx is x to the 4th minus 3x squared plus 1. So what is f1? f1 will be 1 minus 3 plus 1, that's -1. Now, you see that this is a polynomial such that at some point the derivative will be 0, right? So we know that when we do the derivative here, we don't need to look for pattern because eventually it dies down anyway. the fourth derivative of x is 24. So the fourth derivative at 1 will be 24. But the fifth derivative and on already 0. Okay, so the Taylor series for fx equals to that x to the fourth minus 3x squared plus 1 will be equals to, we can spell it out actually, so it will be -1, that's for the 0th term, plus the degree of 1, -2 over 1 factorial x minus 1, plus 6 over 2 factorial x minus 1 squared, plus 24 over 3 factorial x minus 1 cubed, plus 24 over 4 factorial x minus 1 to the fourth, and we stop there. That's what it looks like. Okay, now how about number 15? Oh, they want us to do the associated radius convergence, but that one, the thing is number 13. Number 13, the series, the Taylor series actually terminate, right? So the radius of convergence will be infinity. Yeah, the radius of convergence will be infinity. Okay, if you don't believe me, you can do the following. If you really expand this, like you do the binomial expansion for this guy, and then you basically combine like terms here and there, you will end up with this. You see what I mean? Okay. That's what happened with polynomial functions. Polynomial functions, then the Taylor series and Maclaurin series expansion will be finite. Okay, it will terminate, and the radius of convergence therefore is infinity. Number 15, Taylor series around a equals to 3 for fx equals to ln x. Let's see, hopefully we can get some pattern. Fx equals to ln x. So f3 is ln 3. The derivative will be 1 over x. So f prime 3 will be 1/3. F double prime x, that will be -1 over x squared. I hope I can get some pattern. And then the third derivative will be -2, so it becomes +2 over x cubed, is it right? Right? This is the same to negative x to the power negative 2. Okay, so this will be 2 over 3 cubed. Let me do the derivative again, the fourth derivative. Hopefully I can see some pattern. This will be negative 6x to the negative 4. So the fourth derivative at 3 will be negative 6 over 3 to the fourth. Okay, now I want to rewrite it this way then. This is equal to negative 3 factorial over 3 to the fourth. This is positive 2 factorial over 3 to the fourth. 3 cube here. This is 3 to the fourth here. This is negative 1 factorial over 3 squared. I hope I can get some pattern that the nth derivative at 3 will be when the n is odd, the coefficient is positive. So that's n plus 1. And then this will be n minus 1 factorial over 3 to the n. Is that right? Okay, let me use n minus 1 here. That's also fine. Or maybe I keep it n plus 1. So fx equals to ln x around 3. That will be 0 to infinity of negative 1 n to the 1 n minus 1 factorial over 3 to the n and factorial x to the n. You know what? I don't like this. I don't like this because my f, this guy here, when n equals to 0, it's ln 3. So let me shift that a little bit. I will start from 1. I will start from 1. I will start from 1, but the first term will be ln 3. Okay, but we can simplify a little bit. Ln x around 3 will be, oh, you know what? I make a mistake here. It should be x minus 3 to the n. So that will be ln 3 plus the infinite sum from 1 to infinity, negative 1 to the n plus 1. And then over, see, this guy here cancels, becomes only n on the denominator. 3 to the n times x minus 3 to the n. The radius of convergence will be done by ratio. By ratio the nth term, I will ignore the alternator, and x minus 3 to the n plus 1 over n plus 1, 3 to the n plus 1, multiplied by the reciprocal n 3 to the n over x minus 3 to the n. Cancel this and that, I get x minus 3 over 3 times n over n plus 1. Now, this is convergent to, well, maybe I write it this way first. That is equal to x minus 3 over 3, 1 over 1 plus 1 over n. And this is convergent to x minus 3 over 3. Now, this is less than 1 when x minus 3 is less than 3. So the radius of the convergence is equal to 3. Let's experiment with one more. Okay, let's experiment with one more, and then we go quite hard. Okay, maybe number, you choose 17 or 19. 19, okay. So we have number 19, Taylor series. Around x equals, a equals to pi for fx equals to cosine x. So the fx is cosine x. So f0, f pi will be -1, right? And then f prime x is negative sine x. So f prime pi will be 0. F double prime x is negative cosine x. F double prime pi is 1. The third derivative, that's sine x. F triple prime pi will be 0. The fourth derivative of x is cosine x. The fourth derivative at pi is -1. So we see that for now, fx, which is cosine x, will be -1 plus 0x over 1 factorial. Yeah, it's alternating. That's right. Plus 1 x squared over 2 factorial plus 0x cubed over 3 factorial plus, actually minus 1x to the 4th over 4 factorial and on. So you see the alternating from degree of 0. At degree of 0, I make a mistake, big mistake. I'm sorry. I make a very big mistake. It's supposed to be x minus pi. X minus pi. Supposed to be x minus pi. Okay, so x minus pi squared, x minus pi cubed, x minus pi to the 4th. Okay, you know what? Let me get rid of the 0 term first. So it will be -1 plus 1 over 2 factorial x minus pi squared minus 1 over 4 factorial x minus pi to the 4th and on. So the series, I will start from 0, huh? But we start from negative, so this will be n plus 1 here. Okay, and then it will be x minus pi to the 2n over 2n factorial. See, the exponent for x minus pi, so sort of 0, 2, 4, 6, 8, and on, right? So it's following 2n, and the denominator is following the exponent factorial, right? So that will be the expansion. That will be the expansion. You know what? Let me go on. Let me go on. I want to go on. I want to go on. I want to do, oh, you know what? How about the radius of convergence by ratio? So I will ignore the alternator. Okay, so that will be x minus pi to the 2n plus 2. That's the next term over 2n plus 2 factorial times the reciprocal 2n factorial over x minus pi to the 2n. That is equal to x minus pi squared over 2n plus 2, 2n plus 1. Oh, this converges to 0 as n goes to infinity. So the radius of convergence is infinity. It's for every x. For every x, this series is convergent. Okay, okay. Number 29. I start to love this. Number 29. They say use the Maclaurin series to find Maclaurin series for this. Maclaurin series for fx equals to sine pi x. Now let's take a look on Maclaurin series for sine x. For y equals to sine x, the Maclaurin series is x to the 2n plus 1 over 2n plus 1 factorial. Is it right? Now, so if you replace the x by pi x, do substitution again. Which is equals to -1 to the n, pi to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. Is it okay? It's just that easy, right? Just that easy. Some side note before I give you myself a break, some side note. You can think of this as a sidekick. Yeah, it's not in our textbook. Oh, it is actually. It is in our textbook, but they don't really. Yeah, they don't really show that. Side note. Can you find the value of the 21st derivative at 0 for fx equals to sine pi x? Can you find that? Now, note that we have this pattern, right? -1 to the n, pi to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. That corresponds to the 21st derivative at 0 over 21 factorial x to the 21st. You see what I mean? Okay. So by doing matching, 2n plus 1 equals to 21 implies n equals to 10. Right? In other words, the coefficients, -1 to the 10, pi to the 21 over 21 factorial is equals to the 21st derivative at 0 over 21 factorial. On the left-hand side, we get pi to the 21 over 21 factorial equals to the 21st derivative at 0 of that function over 21 factorial. Therefore, the 21st derivative at 0 of that function is pi to the 21. Okay, I take my break. I come back at 9 o'clock.